So integrating, so differentiating with respect to z. And this is the derivative of h2 with respect to z. I don't have to use partial derivative notation because h2 is just a function of one variable. So that should be equal to the third component of our vector field. And again, we should only have a function of z remaining after all the cancellations. Otherwise, we did something wrong. So now we can recover h2 by anti-differentiating with respect to z. And we would get z cubed up to a constant of integration, which I could make anything, really, so I can make it 0. Okay, so now we finally have our 0 form, if you will, a real valued function. h2, we found this to be z cubed. Okay. So notice that how this, the generalized Stokes theorem, how this is. So this is our 0 form. And this was our original 1 form, the work integral. From, where is it? Yeah. Okay. So this was our original 1 form. Okay. So then apparently this, well, I won't write them down, but our work integral is equivalent to the 0 form, but evaluated at the boundary. So the boundary was, we were integrating over some circle from here to here at the point 0, 0 minus a to the point 0, 0 a. And it didn't really matter what path, right? Because it was a conservative vector field. Okay, so this is going to be f at the terminal point minus f at the starting point. Okay. So that just turns out to be z cubed minus z at the, so at the terminal point, our function evaluates to a cubed minus at the starting point. Okay, so that's the fundamental theorem of calculus for line integrals. So what's the kind of next fundamental theorem that you used? So there was Green's theorem. So this would be restricted to some region in R2. As long as you have a kind of simply connected region. Okay, so we have a region, let's call it M, and then we have a positively oriented boundary for that region. Okay. So okay. So omega is going to be a 1 form on R2. And, that is to say, it's a work integral, right? It's a p dx plus q dy. So if you'd like, it's some vector field dotted with dr. Okay. So that's going to be the integral over that. And sometimes you see this written like so, right? To remind you that this is a closed curve and it's oriented counterclockwise. And this is equivalent to the exterior derivative. So that's going to turn out to be, so let's quickly compute the exterior derivative here. So we differentiate p with respect to x dx plus derivative of p with respect to y dy. So you differentiate the first component, you take the differential, total differential, and then times dx. Plus, and the same thing for q. You differentiate q with find its total differential, and then wedged with dy. Okay, but then what's dx wedge dx? What if you have any differential form wedged with itself will be 0. So dx is 0. Then we have dy dx. And likewise here, dy wedged with dy is 0. So we have partial of q with respect to x dx dy. Okay, and then we know that the wedge product of differentials is anti-commutative, right? So if you switch the order, you get the negative. So doing that, I can get this whiteboard to react. Okay. We would switch these two. So instead of dy dx, we'd have minus the derivative and then dx dy. So that's this is in canonical order, x and then y and then z. Okay, so putting that together, you get the well-known Green's theorem, where this would be partial of q with respect to x minus the partial of p with respect to y, dx dy. Okay, so that's Green's theorem. Maybe we can do an example. Okay. So suppose you want to do the, like you have some triangle. So this is our boundary. That's the perimeter of that triangle. And M would be the triangle itself, yes. The interior, I guess. And suppose you want to do an integral over the boundary of that triangle, and you're integrating minus y dx plus x dy. We could have picked something more complicated, but whatever. So according to Stokes' theorem, Green's theorem, so p is the thing that multiplies dx, and q is the thing that multiplies dy. So this is the same as the integral over that triangle of the derivative of q with respect to x, so that would be 1, minus, and then the derivative of p with respect to y, that's negative 1. So that gives us a 2. And then integrating the differential area element over that triangle just gives us the area of that triangle. So 2 times the area of the triangle, which is 1/2 base times height. So AB. And so I guess if we had time, I would ask that you confirm Green's theorem. So that means you would have to actually do this integral on the left, and you would use you would have to parametrize each segment of this this triangle, each side of this triangle. So for example, C1, you can easily parametrize that where the x would be t and y would be 0 because we're on the x-axis. And t goes from 0 to a. Okay. So dr, let me just write it that way, which is r prime dt would just be, or if you maybe have been easier if I said x equals t and y equals 0, therefore dx equals dt and dy equals 0. And then you can easily do this integral over C1. Where you'd have your parametrization in terms of t. Y is equal to 0, dx is dt, x is t, but dy is 0. So this integral will just give you 0. So then like C2, we can say that x is fixed at a, it's constant, and y is equal to t, where t is between 0 and b. So dx is 0, and dy is dt. So then our integral over C2 we just apply the parametrization. Y is t, dx is 0, x is a, and dy is dt. So we just get at from 0 to b. So you get ab. Okay. And then it turns out that I'm not going to do this one, but it's pretty simple. C3, if you do that integral, you get 0 as well. Okay. So then adding those 3 results up, integral over C1 was 0. Integral over C2 was a times b, and integral over C3 was 0. So you still get a times b. Okay. So that was an example of Green's theorem, which again is just it's a manifestation of the generalized theorem calculus. Okay. Okay, so after Green's theorem, we look at a specialized case of Stokes. So this is just sometimes called Stokes. It's not the generalized Stokes theorem. Okay, so this is where you have some surface in space, and then you have a boundary, and the kind of orientations have to match. So if the unit normal to the surface is like that, we have to think of the boundary as having a orientation that matches that one. So it's like using the right hand rule, right? If your hand curls along the boundary, your fingers curl around that boundary, your thumb would be pointing up. Okay. So they have to have kind of matching. So the orientation of the surface kind of induces an orientation for that boundary. Think of it as the right hand rule. So now Stokes, okay, this will be okay. So here omega is going to be a one form on R3. So it's a work integral, right? This is a work integral. So it'll be one form. And the exterior derivative is going to turn out to be it's going to be the curl. So instead of doing the exterior derivatives, I would differentiate this with respect to x, y, and z, x, y, and z, x, y, and z, and then do the wedge products. Maybe I should. Maybe I won't. Yeah, you would get essentially something that is a two-form corresponding to the curl of that vector field. So let me just quickly. All right, so you would get right, and this would be dx. 1 second, what would that be? So this would be dz dy, yeah? Well, actually, we'll just look at that later when we look at differential forms to see how a curl corresponds to the exterior derivative of a one form. But for now, we just know it's some two form corresponding to the curl of, so I better not write equals, curl of the vector field. Okay. So it'll look like this. The integral of f dr over the bounding curve is equivalent to the flux of the curl of the vector field through the surface. Okay. Okay, so let's see this in action. So suppose we have a vector field. Okay, and we have a surface. So I'll just call it S, that's fine. And that surface is given by A and Y plus Z equals some number A. Okay, so of course, the first inequality tells us we have a cylinder of radius A, Okay, the second equation tells us we have a plane which intersects the YZ plane and the line. The line would be y plus z equals a, so that we have the x, the y and the z intercept are both a. So that's the line. But of course, that's a graph in R3, so that's gonna, you let x be anything, and that gives you a plane which cuts this cylinder in some sort of elliptic thing. So our surface is actually this ellipse that's slanted in space. Okay. So we want to find the work integral over the boundary of this surface. So where the curve is going to be oriented in that fashion. Right. Okay. So we want to integrate over the boundary of that surface, i.e. our ellipse, and we want to find the work integral. Okay. And so instead, and we could, I mean, I tried it and it works. You could try to parametrize that boundary. It wouldn't be that hard, but the integrals are kind of nasty, right? So instead, let's invoke Stokes' theorem and say that that's the same as the integral over the surface bounded by a curve, so the green region. And we would integrate the flux integral of the curl of our vector field through that surface. And here we have to pay special attention to the normal vector to that surface. The unit normal has to match the orientation of the curve. So if you use the right-hand rule and you curl your fingers in the direction, your unit normal would be pointing up like that. So that's going to have a positive y component and a positive z component. So let's quickly compute the curl of our vector field. Okay, so the derivative of x cubed with respect to y minus the derivative of that with respect to z is 0. Okay. All right, so the derivative of x with respect to z minus the derivative of negative x cubed with respect to x, so 0 minus 3x squared. And finally, for the kth component, derivative of this with respect to x minus the derivative of that with respect to y. So that would be 3y squared. So we have the curl. Now to get ds, remember what we have to do. ds, the differential surface area element with a unit normal, is equivalent to if you have a parametrization. So let's think of a parametrization for that surface. I think it's pretty obvious that since we're inside the cylinder, we can parametrize. So let's parametrize S with using x and y. So x and y just be themselves. Okay. But if you look at this plane, we see that z would have to equal to a minus y. So z would be a minus y. And we just the the parameter space would just be that disk of radius A. Okay. So if we have this parametrization, as long as we make sure that the orientation of the normal is right, this is the derivative of r with respect to x, crossed with the derivative of r with respect to y, let's say dy dx. So that cross product of those two derivatives should be simple enough. So differentiate r with respect to x, differentiate r with respect to y. Take the cross product. Okay. All right, so now we're ready to do the right-hand side here of Stokes' theorem. So we have the integral over S, curl of F, dotted with that differential area element with unit normal. So we have the curl computed already, the curl of F. And then start it with ds, which was this cross product, dy dx. Okay, and so since we're integrating, well, so this would now be in parameter space, so my bad. So the parameter space is that we're integrating in the xy plane over that unit, over that disk of radius a. So it's obvious that we should use polar coordinates. So this would become 3r squared. Differential area element in polar is r dr d theta. And theta goes from 0 to 2 pi, and the radius goes from 0 to a. Okay, so we get what? We get 3/4 a to the power 4 if we integrate with respect to r, and we get 2 pi when we integrate with respect to theta. Okay, so that would be our final answer. So that would be much easier to do than actually computing that work integral directly, as it turns out. Of course, we could also confirm Stokes' theorem by doing both sides, but we're not. Okay. All right, so what's after Stokes' theorem? What's another big fundamental theorem of calculus? Let's see. I guess divergence theorem? Okay. So we can look at divergence theorem. Let me just clear this out. Okay, so divergence theorem. You have a manifold that's three-dimensional. So that's going to be, you can think of it in R3 as being a solid. That's M. And then the boundary of M is just the surface bounding that region, the three-dimensional region. Okay. Okay, so turns out that this differential form here is going to be a 2 form on R3. Okay, and it's going to look like, so if you have a vector field F with 3 components, the corresponding 2 form would correspond to something like something where you get flux integral. So that would be actually, so dx dy would get multiplied by r. So it's kind of weird. It's the one component that the z component, because that's the one that's perpendicular to dx dy, geometrically speaking. And then you have dy dz. So what component of our vector field would get multiplied with dy dz? It'll be the x component, right? Because it's perpendicular. So that's hard to describe, I guess. But if you have a cube in R3, right? So you think of dx dy as that bottom face in the xy plane, like a differential area. And we just care about the flux, so we care about the component of the vector field that's perpendicular to that, and that's the z component. Right. Okay. And then we have dz dx. And what would multiply that is the y component of your vector field. So dz dx, this is a differential area element. We want just the component of the vector field that's perpendicular to that face. So that's the y component. Okay. And the exterior derivative we see is going to be a 3 form on R3. So it's going to be, well, if you do the exterior derivative and you differentiate this with respect to x, y, and z, only the z derivative with respect to z would be non-zero. Okay, and well, we'll do that later. So this would be okay. So we can do that actually, that exterior derivative later when we maybe talk about differential forms more closely. But, oops, notice that this is exactly the divergence of your vector field F, right, with components P, Q, R. You differentiate each component with respect to the corresponding spatial coordinate, and then add it all up. Okay. So this Stokes theorem gives us that the integral of the flux integral over that surface is equivalent to the, so let me just make sure, write it that way. So it's a double integral. It's over a surface, and it's a closed surface. It's the same as the integral over the bounded region, so that's a integral over a 3-dimensional region, triple integral, of the divergence of your vector field, dv, say, for differential volume element. Okay. So again, this is another manifestation of the generalized Stokes theorem here. Okay. All right. So maybe we can do an example with divergence theorem where we're going to confirm divergence theorem. So we have a vector field. Do I really want to confirm? No, not really. So here's our vector field. And we have a solid object. Let's call it M, I guess. Okay, so it's not unlike the previous one. It's just a cylinder. Where we have a cross-sectional disk of radius A, and then Z is between 0 and B. Okay. And so we can consider the bounding surface, so that would consist of the side of the cylinder together with the two bounding disks. So you have the bottom and then you have the top. Yes. Right. So you have three different pieces, right? And maybe you're interested in computing the flux of this vector field through that surface. So that's our flux integral in terms of physics through the cylinder. So we can just say, well, nothing goes wrong here. So I guess, I'll mention that later. So we can integrate over the solid cylinder instead, and according to divergence theorem, we integrate the divergence of our vector field instead. Okay. So the divergence of our vector field is simple enough. The derivative of the first component with respect to x, the derivative of the second component with respect to y, the derivative of the third component with respect to z. Okay. So we get a triple integral of z over that region. And so I guess cylindrical coordinates is the most natural thing to do here. So to integrate over the disk, let theta and theta go from 0 to pi, r goes from 0 to a, z goes from 0 to b. And the differential volume element in cylindrical coordinates is r dz dr d theta. So let's see, with respect to z, we get half z squared at the upper bound minus the lower bound. With respect to r, and with respect to theta. Yeah. Anyway, so using these kind of fundamental theorems of calculus, it's kind of weird, but sometimes you have a complicated integral over some boundary, and you instead find, because you're differentiating some sort of derivative, it's easier to integrate over the region bounded by that boundary. Okay. Okay, let me try this one instead. Yeah, there you go. Cool. All right. So that was an example of, well, I didn't confirm. I don't have time. So I guess I'll do another divergence theorem one, where suppose you have a hemisphere that's the upper hemisphere of some So you have a hemisphere, and let's say we want the upper hemisphere. Right, so oops. Okay. And we want to compute the flux of some vector field through the upper hemisphere. Let's call that H. Yeah? So at the end of the day, you just want to compute the flux through the upper hemisphere. So notice I'm not including the disk on the bottom. Yeah, the circle. And you have a vector field. Where is it? Where the heck is my vector field? Oh, yeah. Okay. So why can't we use as it stands? Why can't we use divergence theorem? Right. So why can't we use divergence theorem if we want to find the flux of the vector field through that upper hemisphere? Does anybody know why we can't use divergence theorem as it stands? Right, so remember that divergence theorem says that the flux integral over a closed surface so you have the surface is enclosing a three-dimensional region. Oops. Okay. Yeah, so the problem is that since we're not including that bottom disk, let's call that disk on the bottom D. Right? So our surface consists of a disk. Well, hold on. It doesn't include this disk. Right. Our surface is just the upper hemisphere. So. H. So we can't use divergence theorem as it stands, but notice that we could compute the flux through the disk as well. Okay, and then we could use the divergence theorem. Oops, that's because we've enclosed our surface is now closed. It bounds a finite three-dimensional region. So that would be the integral over that half ball. Half ball, how about that? Okay. And now we can apply divergence theorem. Okay. So let's just compute the triple integral there over the half ball with this unofficial notation. Okay, so the divergence of our vector field, the derivative of the first component with respect to x, the derivative of the second component with respect to y, plus the derivative of the third component with respect to z, dv. So what we get is you don't even have to do this integral, right? Because it's the triple integral. We're integrating the differential volume element. So we're just going to get the volume of this half ball. So that's going to be 2/3 pi times radius squared. Right, so this is just the volume of our half ball. Okay. All right. So we get this integral on the right-hand side of divergence theorem. Okay, and now let's find the integral over that disk. Okay. So what should I should have mentioned before, because we were talking about orientations, is that when you have this differential surface area element, which is like a unit normal times the area element, that normal has to be outward pointing in divergence theorem. It has to point away. It has to point away from the interior of your enclosed volume. Okay, so that's important. And ds is that unit normal to the surface times differential area element. This is outward pointing. Okay, so that's important here, because if I were to integrate over the flux integral over the upper hemisphere, my normal would have to be upward pointing, right? But if you're computing the flux integral over the bottom disk, that normal is downward. Okay, so what we're going to do is we're actually going to compute this flux integral through that disk. Okay, so we have our vector field F. Oops. Okay, now how can I simplify this vector field if I know I'm integrating over that disk? Wow, okay, it's being wicked. Well, if your D is in the xy plane, correct? So that means Z is 0. That means Z is 0. And I'm making all sorts of silly mistakes. Okay, Z is 0. And now ds, I could try to parametrize the disk. We all know how to do that. So I could say that R is the parametrization of the disk I can do in terms of, let's say, I don't know, the stylus is just not reacting very well. Let's see, let's call that, let's say, T and theta. Right. So I could make x equal to T cosine theta, y equals to T sine theta, and Z would be 0. And then I could compute the derivatives with respect to T and theta and take the cross product. Okay. Or maybe not even that, right? Let me backtrack. So maybe not even polar. I can parametrize that disk in terms of x and y. And Z would be 0 in the xy plane. Gosh dang it. All right. So then I could take the derivative with respect to x and then y, and then take the cross product. Let's see what happens there. So 0, 0. You take the cross product and you just get a z component, which would be positive 1. But that's not the correct orientation, right? So you would have to be aware that in divergence theorem, our unit normal on that disk has to be outward pointing. So it would actually be, instead we'd want to use this. So we get -1. Okay. So it would be 0, 0, -1 dy dx. So integrating over that disk, take the dot product, and we get 1 dy dx. So again, we just get the area of that disk. So pi a squared. Okay. So it turns out that doing the flux through that flat disk is probably simpler, okay, than doing the flux through the hemisphere. And so we just simply kind of capped off that region so we have a closed surface and we can employ divergence theorem. Okay, so to rewrite this, sorry. We want to know the flux of our vector field through the hemisphere, but we don't feel like doing that complicated integral. So instead, we computed the flux through that disk with a downward normal. We got pi a squared, and that's equal to, according to the divergence theorem, 2/3 pi a squared. So now we can indirectly solve for the flux through the hemisphere. So what is that? Negative 1/3. Okay. Okay. So I guess that my last computational kind of example. And maybe, like, what have you learned about differential forms so far? Okay, well, let's just go through think of it formally, right? So let's look at differential forms on R3. As kind of making this concept a little bit more concrete. Okay, so you have a zero form. Okay, and the set of all zero forms we would write as zero forms in R3. Okay, and so that's just a real value function. Just a regular old function. A one form, the space of one forms, we can use this symbol on R3. And that would be, you have three functions, three real value functions on x, y, and z, but then it's like the total differential, right, of something. But it doesn't have to be. So, for example, this could be x z cubed dx. Okay. So that's a one form. So two forms. Where we would have, again, so, and by the way, okay. So if you have a vector field with three components, and somebody wants you to find a work integral, right? Then what we do is we associate that vector field to a one form if you want to do a work integral, if you notice it. So you take that vector field and you associate it to a one form, where the x, y, and z component of the vector field multiply dx, dy, dz. And then the work integral then just can be written as the integral of that one form over whatever path. Okay. Okay. So instead, if you have a two form, that would be it's a little weird looking. So, and there's a canonical order. So dy, so dx, dy, dy, dz, and then dz, dx. So these are considered the positive ones. So dy, dz, for example, would be the negative of dz, dy. Right, and oops, that's I messed up, dx. Okay. So what I meant to say is that dx dz is actually not in canonical form. That would be minus dz dx. Okay. And dy dx is equivalent to the negative of dx dy. Okay. All right. And so if you have a vector field in R3 on R3, and somebody wanted you to compute, and you wanted to do a flux integral through a surface with that vector field, you would associate a 2 form to that vector field. Except you have dx dy, but it wouldn't be like p, right? It would be the z component because it's the one that's perpendicular to dx dy. And then you have dy dz, except it wouldn't be the second component, it would be the one, the x component, so on. And then dz dx, this doesn't have a y in it, so you want the y component. Okay. And then you can say that the flux of the vector field through the surface through some surface S, that would be the integral of this 2 form over that surface. So this must work. Right, so if you want to find work with a vector field, you associate it to a 1 form. If you want to do flux of the vector field through a surface, you associate that vector field to a 2 form in that specific way. Okay. All right. So what can we do? Well, so there's, so if you have a, we already did an example, but if you have a 1 form, okay, just a real valued function, we compute what we call the exterior derivative by just, it's the total differential of f, right? So it's the derivative of this with respect to x, dx, derivative with respect to y, dy, and then derivative of that with respect to z, dz. Okay. And now if you differentiate that, so we started with a, sorry, that was a 0 form. Okay, so we started with a 0 form. We took the exterior derivative, it's just like a total differential. And that became a 1 form. So if you take the exterior derivative of the 1 form, you should get a 2 form. Okay, so here we, if we have the exterior derivative of some 2 form tau, some 1 form tau, my bad. That would be just taking the total differential of f1 and wedging it with dx, if you'd like. I'll use wedge product. Total differential of f2, and then you wedge it with dy. Total differential of f3, and you wedge it with dz. Okay. All right. So in our example, we're taking the total differential of y squared, so that would be 0 dx plus 2y dy, 0 dz. And that's going to be wedged with dx. Okay, and then we take the second component and we take the total differential. and we're going to wedge it with dy. And then the third component, you take the total differential, and you wedge it with dz. Okay. Well, here, of course, these are 0, so the only thing that's going to contribute is right there. So we get 2y, and here the order matters, right? So dy wedged with dx. Over here, this is 0. We get 2y dx wedged with dy. And then what's the wedge of dy and dy? Yeah, so 2x dy wedged with dy is just 0, because remember, the differential form wedged with itself is 0. And this gives me, so that's why this is 0, right? 6z dz wedged with dz is 0. Okay. So now we write this in the canonical order as the dx dy, right? So we have to flip these, and when you do that, you get the negative, what you had before. So you see that at the end of the day, we get 0, the two form that's 0. Okay. And so this reflects a important property that as long as your form is C2, so you know that you can differentiate twice, and those are derivatives that are continuous. Then if you wedge a form twice, you should get 0, as long as you know this is C2, in the sense of the components of the form being C2. So that's an important property. Okay, and so we're running out of time, but that property, for example, can be proved that the curl of the gradient is 0. So if you recall, curl of the gradient of some real valued function is 0 vector, as long as f is C2. Now, so a real valued function is just a 0 form. The gradient is just the total is associated to a 1 form, which is the total differential, right? Yeah, so the gradient would be a vector. I'm going to write it lengthwise. And the differential, the 1 form that we get, would be okay. And now you have a 1 form, and you can associate taking a curl of a vector field with taking the exterior derivative of a 1 form, right? And then we know that should be 0, a 0-2 form, so if you'd like. Okay. So you can actually prove a lot of identities that are difficult to prove using differential forms. Okay. So what's another one? Divergence of a curl, right? So if you have a vector field and you associate it to a 1 form, the curl of that vector field is the same as taking the exterior derivative of this 1 form to get a 2 form. And then taking the divergence of the vector field is the same as taking the exterior derivative of that, the two form corresponding to your vector field. So that would be the same as taking a double. Okay. Exterior derivative, so you should get 0, 3 form. Okay. So again, using this fact about exterior derivatives, this is equivalent to showing that the divergence of the curl of some vector field, assuming the components of your vector field are C2, is just 0. Okay. So, yeah, okay, that's, if you haven't, all right. Do you have any questions? Or is it all clear? Differential forms are really elegant because they generalize all the different manifestations of the fundamental theorem of calculus into one nice theorem. It's a very pretty way of looking at calculus. Okay.
Thank you for today.
Sure.
Yeah, thank you. Is there going to be another review session, or is this the last one?
This is the last one, reviews, and on Wednesday next week. So this is the last one.
Okay, cool.
All right.
Thank you so much.
Thank you.